Mark Srednicki from UCSB to tell us about chaos and thermalization in quantum many-body systems.
Okay, thank you very much. Thanks to the organizers for the invitation. Maybe this should have been next week, given the title of next week's workshop, but I will talk about some issues in chaos. And the symposium here is Chaos and Quantum Field Theory, and I have to apologize for not mentioning much about quantum field theory or really anything. Nevertheless, I think the subject are connected, because to do any calculations in most quantum field theories, we have to put in some sort of regularization, and then they tend to turn into more ordinary lattice type systems that we're more used to in condensed matter. So there's definitely a close connection. So I want to start talking about an older story, and this is how I got involved in this business a quarter century ago now, which disturbs me when I think about how long that's been. But this is both to set up the topics I want to discuss a little later, some more recent work, and also just to review the concepts so that we're all in agreement on what various terms mean. Because what I've discovered in this, over these years of discussion, is that a lot of confusion arises just because different people have different definitions of terms like thermal equilibrium. And if we take the time to agree on definitions, or at least for me to tell you my definitions, this can prevent some needless confusion. So the basic problem I want to talk about is, how do isolated quantum many-body systems come to thermal equilibrium? And I always like to have a simple example in mind. So my simple example will just be a dilute gas in a box, and I imagine my gas consists of atoms with some short-range repulsive interaction. We can think of them as hard spheres, and I'm going to put them all in the lower left corner of the box, moving up. And then we expect a little while later, if we look in the box, we'll find them distributed around the box, and they will have a Maxwell-Boltzmann distribution of momenta, or if we're in some quantum regime, maybe we need to do Fermi-Dirac or Bose-Einstein. Also, quantum mechanically, what I mean by this initial state is that I picked some initial state. And if these are really hard spheres, then I could imagine using Gaussian wave packets for each one that localize them in both position and momentum. But some sort of initial state, which we would all agree is not an equilibrium state. And then we want to just time evolve with the Schrodinger equation, and later find something we would agree is an equilibrium state or not. So how can that happen? So some basic assumptions. I'm going to assume I have a large number of degrees of freedom, n. Doesn't matter precisely how these are defined. That we have some set of observables, A sub I. A will generically mean some observable. And so for our problem of the dilute gas, and if, and if we describe it in a second quantized way, I could use a number operator for some momentum mode, or maybe some range of momenta that I would integrate over. And of course, since we're doing quantum mechanics, we have to have a quantum state, and I will always work, well, not always, but for now, we will work in the Schrodinger picture, where the quantum state is time dependent. And I will also assume that the thing to look at is the instantaneous quantum expectation value of an observable. So again, in general, we would want a list of observables. but I will only talk about one of them. They don't have to commute. They can, we could also have number operators for some range of position if we wanted to do that. Okay, and again, I will assume the thing to look at is the instantaneous quantum expectation value. If we're interested in quantum fluctuations of this observable, then we could put a squared on our list. So we would look at both a and a squared, or indeed all powers of a, if that's what you want to do. I do want to have in mind that these observables are somehow physical, that they are something one could imagine measuring, or maybe a theorist can imagine measuring. I don't insist that they actually be experimentally measurable in a real experiment, but also I don't want to allow things that I just make up mathematically, like specifying some matrix in the energy basis, matrix element by matrix element. I want them to have some sort of physical status. In a lattice system, maybe they would be local observables on the lattice, for example. Okay. Then there's a total energy, which I will define as the expectation value of the Hamiltonian, which is time independent. And I will assume that we are in an energy regime where it's scaling with the number of degrees of freedom n. So we'll want to think of n as very large, but I don't want to take the n goes to infinity limit, because different things scale with n differently. But I do want to think of it as large, and I want to think of the energy as scaling with it. Because it's quantum mechanics, there's a quantum uncertainty in the energy, unless we're in an actual energy eigenstate, which is given by this standard formula. And I want to assume that this scales slower than n. So if we say energy, something scaling with n is extensive, I want my energy uncertainty to be sub-extensive. So for example, for a thermal density matrix, if I use that as my state, here I've restricted myself in the notation to pure states. We could also talk about mixed states. But if I used a thermal density matrix, we would get this with gamma equals 1/2. So the uncertainty in the thermal energy scales like the square root of n. And these are some mild restrictions on the state. At least I think of them as mild. Then I will define a usual canonical thermal expectation value in this, because there are going to be lots of different brackets here. I have to have some unusual notation. So I will define A in square brackets with this subscript as meaning the thermal expectation value of the observable, the canonical thermal expectation value, excuse me, where I fix the inverse temperature by requiring that the thermal expectation value of the Hamiltonian be the energy. So this, which is given by this formula up at the top with the quantum state. And now comes my definition of thermal equilibrium. We, or I, maybe you won't want to agree, but I will say that the system is in thermal equilibrium at time t, if at that time each of the quantum expectation value for each observable is equal to the thermal expectation value to within some error. Right? We can't insist that this be a mathematically precise equality, but to within some tolerance that again would be set by experiment in a realistic situation, and that this is true for each of the observables that we put on our list. So, okay, and so I want to note that this is a time-dependent definition. Some people like to use definitions of thermal equilibrium that are time-independent. And so it can be true or not true at different times. So if all the air in the room spontaneously moves into the corner, then at that time, I would say by this definition, the air in the room is not in thermal equilibrium, even if that's just a spontaneous fluctuation. So I'm allowing sufficiently large fluctuations to take us out of equilibrium by this definition, which I think has to be practically true, right? If you walked in, if you had a box and you found all the gas in the box was in the lower left corner, all moving up, you would not say that gas is in thermal equilibrium. All right, so what do we expect to happen? Again, my observable will be something like the number of particles with a certain momentum. And I want to start out in a state which is not an equilibrium state. So the expectation value of this observable will be far from its thermal equilibrium. But then if we follow it in time, we expect, because we took a class in statistical mechanics or because we live in the world and watch what happens, we expect this quantum expectation value to move towards the thermal expectation value and then stay there most of the time. And this is an artist's conception here. This is jaggedy line is supposed to indicate that, you know, there are fluctuations, and indeed, we can imagine that at much later times, there might be large fluctuations corresponding to all the air moving into the corner. But at most of the time, we would expect the quantum expectation value to be close to the thermal expectation. So that this, you know, times here, we would satisfy the definition of thermal equilibrium on the previous page. My setup here is not showing me the chat page, by the way. So if someone has a question, shout it out. Okay, and so the question I want to ask is, can we get this picture can we derive this picture without placing any further restrictions on the initial state? I want to allow myself to have a very broad range of initial states, conditioned only on giving a certain expectation value to the energy and an uncertainty in that expectation value, which is small in the sense of scaling with n. So really here just setting up notation, we'll have some energy eigenstates that I'll designate with this index alpha. Then time evolution is just given by an initial state, which is set up by some coefficient C sub alpha. And then we get these phases, time-dependent phases, and I am betraying my roots as a high energy theorist by leaving out the H bar. I've set H bar to 1. And then we can compute this quantum expectation value, or at least write down this formula for it. And I've broken it up into two terms, a term with only the diagonal matrix elements and a term with the off-diagonal matrix elements. And again, we have this formula from quantum mechanics, and we have this picture from our understanding of what we think should happen in a real world system. And we would like this formula to agree with this picture. And so how can we get that to happen? Oops, sorry. Okay, so if we stare at the formula and stare at the picture, in the formula, this first term has no time dependence in it, whereas the second term has time dependence and has phases that oscillate, and so will produce oscillations in time. If I look at the picture, the time independent part of the picture is this thermal expectation value. So that leads us to expect that we should equate the first term with the thermal expectation value, and then the second term will give us the fluctuations or deviations of the graph from the expectation. Okay, and now we have an immediate puzzle, which is this thermal expectation value doesn't know much about the state. All it knows is the total energy of the state through the inverse temperature, which is chosen to give the correct expectation value of the energy. Okay. So the problem is this term looks like it depends strongly on the initial state because it's got all the C alphas in it, which tell me what the initial state is. So how can these two things be equal? And a possible answer is if these diagonal matrix elements in the energy basis of our observable vary smoothly with the energy, as shown here in another artist's conception, then we can plot on the same graph the C alpha squareds. And remember, we've chosen our initial state to have quantum energy uncertainty, which is small in a suitable sense. And the sense in which we want it to be small now is that over this delta E range where the C alpha squareds are non-zero or significantly non-zero, that the A alpha alphas don't change much. So now it's not going to matter what the precise C alpha squareds are, because no matter how we weight these blue dots with a red dot, the blue dots are all about the same. So we're going to, for these red dots and these blue dots, the expectation value that we get by multiplying red dots by blue dots is always going to project on, is going to, in this case, project onto the left and give me this number of around 4. Okay. So we come to a conclusion. If the diagonal matrix elements vary smoothly with alpha and the quantum uncertainty is small, then this sum over the product will only depend on the total energy. And furthermore, has to equal the thermal expectation value. There was a hand raised. Does some,
yes, I have a question. So my question is that when we normally think about thermal equilibrium, we think of equilibrium between two different systems or two subsystems. So in this case, I don't see that that separation. What is your subsystem?
Well, one way to think about it is if you think of this observable A as involving only a few degrees of freedom, that would be the subsystem.
Okay.
Right. So I could divide my system, and later I'll talk more about this, but I could divide the system into two subsystems, but for now I want to think of one of those as big and one of them as small. And then my list of observables, here my notation only talks about one of them, but we could have a list of them. I could write down a complete set of observables for the small subsystem, and that would be my list.
Okay, so for example, A could be like measuring the energy only in some finite subsection of the box.
Yes, yeah.
All right, thank you.
Other questions? So I'm not seeing chat, but I do see hands raised. So, okay, right. So this sum depends only on E because of this assumption at this point, this supposition that the diagonal matrix elements vary smoothly with the energy, and the other supposition that the C alpha squareds give me an energy uncertainty, which I can consider to be small on the scale on which these A alpha alphas vary, then this sum will only depend on the energy, which is where these things are peaked. So here the energy is 15 on this graph. We could consider another state where it's peaked at 25, and then we would get a different expectation. And then finally, this is much less obvious, but this actually has to equal the thermal expectation value. And that's because the C alpha, one possible choice of the C alpha squareds is Boltzmann weights. Boltzmann weights, although it wouldn't be obvious on that graph, also give a small energy uncertainty. And that's because of the exponential fall with energy of the weight up against an exponential rise in the density of states, which was not depicted on my pictures. So we know that Boltzmann weights give an energy uncertainty of order root n compared to an energy of order n. So Boltzmann weights satisfy this delta E being small condition. And so that's one possible choice of C alphas I can use. And of course, by definition, that will give me a thermal. But this conclusion is that it doesn't matter what the C alpha squareds are once they've picked out an energy and a small delta E. So again, up to small errors, these two things have to be equal. And this is what is called Eigenstate thermalization. I think I was the first person to use that phrase in 94. A very similar result was given by Josh Deutsch earlier. And naturally, there is a long history of other work predating this, which came to similar conclusions, often in the context of specific models. So again, too long a history to go into here. There's a nice review article from a few years ago by these folks, which I recommend. Okay, so that gives us part one. That explains, again, if the A alpha alphas are smooth, that explains how this, this object, which looks like it should depend strongly on the C alphas, can be equal to this object, which looks like it doesn't. But now we have another, that's not enough. We would like the fluctuations to be small most of the time, right? So here there's a we could call it a fluctuation if this occurred spontaneously. Here it's occurred because we chose a specific initial state. But most of the time we want the jagged line to be close to the dashed line, and that means this term is small. So what needs to be true for that to happen? And the answer is very simple. These A alpha betas, the off-diagonal matrix elements, should be small. If they're small, and again, in a sense to be defined, but if they're small, then most of the time this weighted sum will also be small. But at particular times, with particular choices of the C alphas and their phases, we might be able to get these many terms that we're summing to add up coherently and compete with the first term. So that's what's happening at this peak. We got to choose the C alphas. We chose them deliberately to drive this quantum expectation value away from the thermal value. But once we've done that at time 0, as time evolves, these phases will start showing up, and the coherent sum here will stop being coherent. It will become an incoherent sum. And this, if the A alpha betas are sufficiently small, this sum will become negligible, and we will get back to this. Okay, so that's the basic idea, that if the A alpha alphas vary smoothly with alpha, and if A alpha beta is small, then we can understand how a system comes to thermal equilibrium in the sense I've been discussing. Okay. And so now the question is, does that ever happen? Do we know of any systems in which these behaviors of these matrix elements occur? And happily, the answer is yes, and this is where chaos comes in. These facts are both known to be true with somewhat different levels of rigor for quantized chaotic systems, by which I mean a system that you get by starting with a classical system that's chaotic throughout its phase space, and those are actually fairly rare, but never mind. And then you quantize it by whatever quantization method you like. Okay, and so a nice example that's been historically used a lot are billiard systems, in which here in the simplest case, we have a single particle bouncing around inside a shape. And depending on the shape, we can either get integrable motion where there's an extra constant of the motion in addition to energy, such as angular momentum in the spherical case, in the circular case, individual linear momenta in the rectangular case. But various other shapes give us chaotic motion. And so we have, the so-called Sinai billiard, a circle inside a square, the stadium billiard, the cardioid billiard, all of these are proven to be chaotic with various definitions of what we mean by chaos. I don't want to go into that in any detail. Positively Lyapunov exponent, for example. Okay, but of course we don't want to do classical physics, we want to do quantum physics, and so we want to look at the quantum energy eigenfunctions. And here in a billiard, and I should mention that a gas of hard spheres can be considered as a very complicated 3n dimensional billiard for n particles in 3 dimensions. The quantum energy eigenfunctions can be written as superpositions of plane waves where the different k's all have the same length because the length is related to the energy, but with coefficients that are different. And in 1977, Michael Berry wrote down a conjecture that if you took an actual energy eigenfunction in an actual quantum billiard, these A sub j's would look like Gaussian random numbers. Of course, they're not really random in a sense because you can compute them. You could find your energy eigenfunction and compute it. But that they would, if somebody handed you this list of numbers, they would pass various tests for being random numbers selected from a Gaussian distribution, and importantly, uncorrelated from different k to different k. Okay, so this is subject to numerics test, and here's some nice pictures by Arne Backer from a while back. This is a particular, on the right is a particular energy eigenfunction in the cardioid billiard, and on the left are some random waves where the coefficients were chosen from a Gaussian distribution, chosen randomly from a Gaussian distribution. And you're supposed to look at these and think, gosh, those look alike. Now, of course, we could do more tests. For example, we could actually study the amplitude distribution. And in fact, it beautifully fits a Gaussian. There are not even any parameters here because normalization of the wave function gives us the width. And so again, it works extremely well. Okay, and so more generally, if we move away from billiards to more complicated systems, we need a suitable generalization of Berry's conjecture. And this has been discussed by various people, including me at various times. I don't want to go into details of that. But roughly, if you have a random wave function, and then you construct something like the Wigner function or Husimi function on phase space, a random wave function that's suitably random in the Berry sense will lead to a uniform probability distribution, uniform with respect to the Liouville measure over a constant energy surface in phase space. And this is actually a theorem, Schnirelmann's theorem. The expectation value in an energy eigenstate, what's being called A alpha alpha on the previous pages, if you go to a high enough energy, it will come closer and closer to a classical microcanonical average of that observable over the corresponding energy surface in phase space. Sorry. And to be precise, we need various all right, I have a sensitive arrow button on my laptop. Okay, if the system is chaotic and A is an H-bar independent operator. Okay, and there are various epsilon delta things that one needs to throw in to be mathematically precise, but we're not going to worry about them. But we really need something much, much simpler than that. It doesn't even matter that it becomes the classical microcanonical average, just that it becomes smooth. And so Schnirelman tells us that it becomes the classical microcanonical average, which is smooth. Furthermore, each of these corrections, the first one starts as at order h bar to the 1/2. Those are actually smooth also. So the whole thing becomes smooth. All right, I will give up on trying to go backwards again. The random wave conjecture also tells us that these off-diagonal matrix elements should vary erratically with alpha and beta, because the different energy eigenstates use different random coefficients. We can also work out a sum rule where we consider basically the quantum uncertainty in this observable in an energy eigenstate. That's given by a sum of squares of off-diagonal matrix elements. Now, this should be a number that's order 1, order h bar to the 0. It should not be some huge number. On the other hand, this sum involves a huge number of states. If we put in a density of states factor, there's some e to the average energy in here, or e to the energy beta, I guess more precisely. So that's a huge factor from the density of states. And in order for this whole thing to be small, that can only happen, well, there are a couple of ways it could happen. One is that all these A alpha betas are individually very small, enough to compensate the density of states. Another thing that could happen is a whole bunch of them could be 0. And that's what happens in certain integrable systems where there are lots of selection rules. But without selection rules, and we're not supposed to have selection rules in a chaotic system, these all have to be very small. Okay, which was part 2 of what we needed to have happen. We needed the off-diagonal elements to be very small. Okay, so we can summarize all this by writing down a formula for these matrix elements that is now usually called the ETH, for Eigenstate thermalization hypothesis matrix element formula. There's a diagonal term in which there's some smooth function of energy, energy here being defined as the average of the two energies. Of course, with the Kronecker delta, that means it's just either energy, which are the same. Some smooth function, which is this holographic A here. And then the off-diagonal terms, and also possibly fluctuations in diagonal terms, there's an e to the minus s over 2. That's what we got from the previous part. There's some function that I think of as smooth, that's a function of the average energy and the energy difference. And then there's something, some quote, random unquote factor that we should think of as varying erratically. One could say randomly, but of course nothing here is truly random from matrix element to matrix element. And it will be very useful to think of the energy, again, as scaling with the number of degrees of freedom, but the energy difference as being of order 1, or n to the 0. It will turn out that for many interesting observables, this f function has that property that it cuts off exponentially once omega becomes larger than some number of order 1. Okay. All right, and then of course we have to note that many systems don't obey this ansatz. Integrable systems require generalized Gibbs ensembles that is put forth by these folks some time ago, where we need instead of just e to the minus beta h, we need an e to the minus beta parameter times each conserved quantity. There are also a purely quantum effect of many body localization, a nice review by these guys from a few years ago, in which quantum effects cause the energy eigenfunctions to become localized. Those then acquire an effective quantum integrability. And those things don't thermalize in the sense I've described here. They can there's a more general sense of thermalization where they thermalize to a generalized Gibbs ensemble. But then we need to know the corresponding betas for all the other conserved quantities. Or many of them can thermalize anyway from a large class of initial states. And there's been a lot of work done on thinking about what classes of initial states can thermalize, even for systems that don't have this matrix element structure. Or, of course, in the real world, it is, of course, very hard to actually isolate something extremely well. And so even some fully integrable thing might thermalize if it keeps getting hit by perturbations from the environment. Okay. So that was a review of mostly older work. And part of the reason I wanted to do that was to set the stage for some more recent work that I want to talk about. So, any questions? Okay. Well, in the old days, I would give talks like this and everyone would think it was obviously wrong. And now I give this talk and everyone thinks it's obviously right. So I guess that's progress. Okay, so for those of you who found that all old news, I will talk about now some more recent stuff. The first two papers that I want to talk about, both done in collaboration with my student, Chaitanya Murthy, who has now just begun a postdoc at Stanford. One is on entanglement entropy of a subsystem. And this is closely based on earlier work by Peter Liu and Tarun Grover, and was inspired also by some numerical results by Lev Vidmar and Marcus Riegel. Stop touching my background. Okay, so the basic idea is I have a system which will be described by a Hamiltonian H, and this relates to the question earlier. I'm going to cut it into two subsystems. Subsystem 1 and subsystem 2, and each of those will have their own Hamiltonian, but of course there has to be some interaction between them. And usually I'm going to think of this as some sort of uniform system, like some lattice system that I've cut into two pieces. But we could also think of these as being different systems. The analysis does not depend on them being, the two subsystems being similar. Although that will be mostly what I'm thinking about. And we'll, without loss of generality, take the volume of subsystem 1 to be smaller than the volume of subsystem 2. Or really what I mean is that there are fewer states at a given energy in subsystem 1 than in subsystem 2. Okay, now of course the subsystems have their own energy eigenstates. And here I'm changing, have their own energy eigenstates. And now I'm using Latin letters instead of Greek letters to denote these. Also, it will be convenient to give an additive normalization to this interaction so that its expectation value in the energy eigenstate of interest is 0. Of course, if we just wrote something down, it wouldn't be 0. So I'm going to take that constant and partition that constant and add the appropriate pieces of it to H1 and H2. So this is really a minor technical detail. Okay, now how should we think about our original energy eigenstate of the complete Hamiltonian? Since the energy eigenstates of the two pieces, we assume those form a complete set of states of the whole system. This statement here is really a tautology. It just says that I can write this as some matrix in this product basis. But the idea originally due to Josh Deutsch and followed up on extensively by Liu and Grover is that this should be a random we should think of this as a random matrix. So this is the usual This is again analogous to Berry's random wave conjecture, analogous to applying random matrix theory to chaotic systems. We should think of this as a random matrix, but there should be some sort of envelope function that forces the sum of the two subsystem energies to be equal to the specified total energy. That's what this F function is supposed to be. And then there's a density of a normalization factor which counteracts the density of states. And it turns out the right thing to do is to put in here the entropy of the sum of the two subsystem energies, which can differ from the total energy. And so these refinements are what Chaitanya and I added to this ansatz, which was called the ergodic bipartition ansatz by Liu and Grover. And then again, we're going to think of this C as a random matrix with zero expected value of an element and a square which is normalized to 1, and any other non-1 factors are supposed to go in here. And so what Chaitanya and I were able to show is that for a system in more than one dimension, you can actually compute this function by considering expectation values of different powers of the different Hamiltonians in this energy eigenstate. One can show that it's actually a Gaussian with a width that's given by, not too surprisingly, the energy uncertainty that's introduced by this interaction. So, of course, this spread in energy, the distinction between the sum of the subsystem energy and the total energy, has to be related to the interaction energy. So that's not a surprise. The mild surprise is that you can actually show it's a Gaussian. That only works in more than one dimension due to a central limit theorem type argument. In one dimension, you can still show that this function has a spread that's given by this formula, but you can't show that it's Gaussian. Okay, Liu and Grover pioneered the idea of computing the entanglement entropy now, which we define in a now familiar way by, we can take our initial density matrix, which is this pure density matrix of this energy eigenstate, and trace over subsystem 2. That will give us a reduced density matrix for subsystem 1, or we could do it the other way around. And then the entanglement entropy is minus trace rho log rho, and we can do this either way. We can either trace over subsystem 1 or subsystem 2, and we get the same answer. So to actually attempt to do this calculation, the trace of say subsystem 1 would become, we would take a limit where we can treat this as an integral over the energy with a density of states. Oh, and there should have been a 1 here. This should be the density of states of subsystem 1. Okay, and then as was pointed out by Daimarsky, Lashkari, and Liu a few years ago, an ansatz for this, which they called the subsystem ETH ansatz, is that the density matrix of subsystem 1 should scale with the number of states that got traced out. And that's e to the entropy of subsystem 2 evaluated at the energy that's available to it, which is E minus the energy of subsystem 1. And here that delta parameter I'm treating as effectively 0. I'm not worrying about that correction, which is small in this context. And then there's an overall normalization to get the trace of this to be 1, which looks like that. Okay. So Chaitanya and my contribution to this was to notice that this really only works for computing the entropy if subsystem 1 really is the smaller subsystem, in the sense that its density of states, or entropy, the logarithm of the density of states, is smaller at that energy than the density of states of subsystem 2. If the opposite is true, which can happen even if subsystem 1 has smaller volume, just because we could look at an energy which happens to be large, where subsystem 1 happens to have a lot of energy. If it then has too many states, subsystem 2 is the thing that has now the subsystem 2 density matrix. So really what one should do when doing this integral is switch from subsystem 1 to subsystem 2 at the point where one of them crosses from being the smaller to the larger. And that actually leads to some correction. So here's the formula one gets for the entanglement entropy from that. I've left out the details. S max here is the larger of these two subsystem entropies, either subsystem 1 at energy 1 or subsystem 2 at energy 2. Okay. And now these integrals can be done by steepest descent, basically. There's a point of steepest descent where these entropy derivatives match, and we identify that as the inverse temperature. Then second derivatives are given in terms of heat capacities of the system and the subsystems. And after a bunch of messy integrals, one gets the following formula for the entanglement entropy. There's the usual term, which is the entanglement entropy is just the smaller thermodynamic entropy of whichever system is smaller, subsystem 1 or subsystem 2. And the bar means evaluated at the natural energy split between the two, the equilibrium energy split. But then there's a correction, and the correction is interesting. All right, so probably easier to look at the picture. Here's what we get. The orange lines are what we get from the first term. It just says the entanglement entropy matches the thermodynamic entropy of subsystem 1 up until it becomes the larger system, and then it goes down with subsystem 2 becoming the smaller subsystem. But this extra terms and these entropies all scale like the total volume. The correction term scales like the square root of the volume. And that sort of correction was noticed in numerical results by Vidmar and Wiegel. So we were able to write down this theoretical formula for this. And the gap at this point between the actual curve, which includes this negative correction, and the naive curve, is the square root of the heat capacity of the whole system divided by 2. And then it goes to 0 exponentially fast as the volumes move away from an exact splitting. So I view this as an interesting result that shows that there's more in entanglement entropy than we might have expected. And recently, my colleague Don Merrill and his collaborators have an ADS CFT holographic argument for this correction. So it shows up there as well in a different way, of course. Okay, so that is one of the two more recent results I wanted to tell you about. Any questions? All right, so I will, someone has a hand raised question, a couple of these. Yes.
Can I ask a question?
Yes, please.
So this term over here, phi of S2 minus S1. So why is this expected to be universal for all systems? It seems that
the universality comes from doing these integrals. So at this point, we've approximated discrete sums over states by continuous energy integrals. So one, of course, has to worry about that. But then the non-universality comes into what these entropies are, right? So I have to tell you what the system is to tell you what its entropy is at a function of energy. But once I know that, then and then assuming the usual scalings, that entropy and energy scale like volume, then everything else is just a steepest descent computation where I expand this to second order in energy differences. And then the only things that matter are these first and second derivatives, which somebody in the dim and distant past discovered were heat capacities. So, so at the end of the day, the only thing that matters is the heat capacities. Of course, you know, this all goes back to the statement that the original energy eigenstate could be written in this product basis for the two subsystems, and that the product coefficients would look like this modulated random matrix. And you know, the random matrix part, that's pure assumption from the usual stuff we've seen for the past few decades of quantum chaos being connected to random matrix theory. I would be shocked if those matrices didn't look like random matrices, but you know, we don't know how to prove things like that.
Okay, thank you very much.
Yeah. Other questions? Okay, I'm going to move on to my last topic, which is out-of-time order correlators. Again, this was done with Chaitanya last year. Oh, crap. Okay, so this is a subject which has a history that started in 1969 with Larkin and Ovchinnikov, who considered this in the context of metals, I believe, and then was picked up, sort of dropped. You know, as far as I know, and maybe Thomas or Pedrag knows better, or someone else who's here may know better, this notion of an out-of-time order correlator really did not seep into quantum chaos theory, as far as I know. It then was sort of revived in the context of ADS, CFT, and black holes. I think the Robert Stanford and Susskind paper was the first modern paper to mention it. Alexei Katayev then took this up and gave a couple of talks, which are now, they're at the KITP and are widely referenced. The version I'm going to talk about is the one due to Maldacena, Schenker, and Stanford, which I'll say more about in a minute. There's a good short review on out-of-time order correlators by Brian Swingle in Nature Physics a couple of years ago. There are different ways to define them. We could think of the square of a commutator of operators, one at one time and one at another time. That's a sort of natural context in which it occurs. Larkin and Ovchinnikov pointed out that if you took a classical limit of that, that would now look like a Poisson bracket, and a Poisson bracket could, in many situations, and in particular the one they were concerned with, could have an exponential Lyapunov growth. And so these out-of-time order correlators can have exponential growth. Okay, then there are different ways to regulate them. I'm going to use this way, which was introduced by Maldacena, Schenker, and Stanford, or well, they used it. I'm not sure they were the first to use this. In which we have an operator, and then we're going to sandwich some e to the minus beta h's over z's, some thermal density matrices, but we're going to chop it up into 4 pieces. So a sort of normal thermal correlator would have a single row on the far left, and then A of T, A of 0, A of T, A of 0. For various, mostly mathematical reasons, it's nicer to chop it up in this way. And so by fiat, that's just going to be what I'm going to look at. Okay. All right. And so again, the key feature that these out-of-time order correlators are supposed to have is that at an intermediate range of times, there's some normalization, which I've left out here. But if we normalize it so that after what these guys call the dissipation time, which should be of order beta, the inverse temperature, there might be some transient behavior over that time, but then it should settle down into something that's constant for a while, but starts growing exponentially. And then eventually this will saturate, and so this has to terminate. So we would like a system that has a hierarchy between these time scales, a dissipation time and what they call the scrambling time. Many systems do not have this hierarchy. You need to have a small parameter. In ADS-CFT, where it's dual to a large N gauge theory, the large N of the large N gauge theory is the parameter. There are semi-classical systems where a suitably normalized H bar is the small parameter. But we need that small parameter in order for this to happen at all. Okay, and what Maldacena, and Stanford showed was a bound on this growth exponent lambda. They showed it was bounded by 2 pi over beta. And when I first saw these results, they bugged me because if I dare to go backwards, I think I know everything about this, right? This A of t is some observable, so in a quantum chaotic system, it should satisfy the ETH matrix element ansatz, and then I should know everything I need to know, and so then I should be able to derive this, right, as it says here. Okay. So my goal is to derive this from the ETH ansatz. And for years I was confused about how to do this, but finally with Chaitanya's collaboration, we were able to understand how to get that. So, yes, question?
Well, I would wonder if you do have enough to know how to do it, because here you're discussing a 4-point function, and it's quite likely that you need to refine the ETH ansatz for the matrix elements. For example, you can't assume that the Rij's are Gaussian anymore. You have to allow them to have correlators.
That is absolutely right, and I will come to that. But I claim that non-Gaussian corrections are intrinsic to ETH.
That's fine, but intuitively I would expect that whatever would be conceivable from whatever point of view Shanker, Stanford, and so on used could be translated into ETH language. So
sure, I mean sure, but
so my guess is you'd ultimately need the same proof to get their bound.
I think that's yeah. I mean, if you look at their paper, they make various assumptions.
Yes.
We make various assumptions which seem different. Are they really the same? That I haven't dug into enough to know. For me personally, I wanted to understand what I needed to know about the ETH matrix elements to prove the statement. One can, of course, regard that as not adding anything, because if what you want to know is the bound, we already have a proof, and so there's no need to go any further.
Well, I'm skeptical that there's going to be a proof that doesn't use the same properties of analytic functions that they used.
Okay, well, I will show you. I'm actually going to omit most of the details, but I invite you to look at the paper.
I did a little bit.
Yeah, but I'm going to sketch how it goes here. So, so for simplicity, I'm going to set this diagonal term to 0 because it doesn't actually play any role. And we could always just subtract it off by defining an observable with it subtracted off. Then a simpler object is the corresponding 2-point correlation function, which is written here. And plugging in the ETH ansatz, we get this. Again, I'm going to assume that I can do these sums by averaging the Rij squareds over small intervals, and that the average over a small interval in both EI and EJ will be 1. Again, that I can translate the sum into an integral, and then we get the following messy looking integral. Here I've also changed to E and omega notation, where E is the average of the two energies and omega is their difference. Then we get these different density of states factors. And again, assuming this F is a smooth function, which is really equivalent to assuming I could do this average here. And again, assuming the usual large N scalings, I can Taylor expand these with the usual derivatives, and I get this formula. And so this is a formula which has appeared in the literature in various contexts. This factor we can neglect because C is again the heat capacity, which scales like the volume, and I want to take the volume to infinity. So this just becomes a 1, and I just get the Fourier transform of F squared for this 2-point function that's regulated in this way with the square roots of that. Okay, now if we go back to that formula, it turns out that the what we might think of as a regular thermal expectation value of A squared, the trace of rho A squared, is equivalent to that correlation function F2 at an imaginary time, at a time of I beta over 2. So formally we get this expression. But this should be finite because this, again, here I'm thinking of A as some spin-like observable that whose square is bounded. And so the trace of this should be finite. And so that tells us that this F function has to decay at least this fast at large omega. Okay. And here is the 4-point function. Actually, this is a generalization in which I use 4 different times for the A's. One of them at 0, and then 3 at 3 different times, T1, T2, and T3. The omegas are energy differences between I and J, J and K, K and L. And if I plug in the ETH ansatz, I'm then going to have to do some statistical average of the product of 4 R's with their indices paired up like this. And so the Gaussian case would be just these 2 Kronecker deltas. But there are, in general, corrections. And a very nice paper by Laura Foini and George Kirchen from a couple year ago, really clears this up very nicely. And so I would say the key to understanding this is their general analysis. So they gave a very general analysis of how these higher order subleading corrections should work. And it looks subleading because it has a factor of e to the minus s. And of course, this is an s scales like the volume or number of degrees of freedom. So this is exponentially small. But in fact, it's just as important as these other terms, because what these Kronecker deltas do is set one energy to another. And so when I do my sums over the energies, one sum gets omitted and translated to an energy integral that omits an e to the plus s. So these Kronecker deltas are actually just as small as this. And this g function is in general an unknown function. There is not something we can do to figure out what it is that's not system specific. It's just like the f function, it's a system and observable specific function that has to be, to the extent it's possible at all, calculated on a case-by-case basis. But it is the key to the out-of-time order 4-point function. These other contributions, for a reason I will not try to explain here, are not the important contributions. The important contribution to the out-of-time order 4-point function is this one. Now, it turns out that if one considers the object trace rho a to the 4, that can be expressed as this 4-point function with various imaginary times, and then various integrals, which fill up multi-lines if we try to write them down, have to converge. And that turns out to allow us to consider, to put a limit on the asymptotic behavior of the G function when one of the omegas becomes large and the others are held fixed. And this is what it turns out to be. And this G function is, roughly speaking, the Fourier transform of the time 4-point function. And with some modest caveats on the precise functional form of the time-dependent 4-point function, one can translate from this bound on the behavior of the G function in frequency space to the bound on lambda in real-time space. Okay, so is this the same proof as the original? I think they're different. I think they make different assumptions, but if one really digs into it, it may be that all the assumptions are secretly the same, or that going through the proof more carefully, one requires everybody's assumptions to be true. Anyway, let me go back also and say something about these small corrections. Foini and Kirchen referred to them as corrections to ETH. This is, of course, nothing but semantics. But from my point of view, I think they're really implicit there, because the way they argued for these, I would say, is really a generalized version of Berry's conjecture. They said that what one should look at is the unitary rotation from a basis that diagonalizes the observable to the energy basis. And their key assumption was that that unitary transformation is looks like a random unitary transformation within restricted ranges. So we want to restrict both the energies and the observable eigenvalues to relatively narrow ranges, and then look at that unitary transformation and treat that as a random matrix. And that will tell you that these correction terms have to be there. Another way to see it is if you just think of the I and J indices as standing for random wave functions, you see each index appears twice. So there's going to be like a psi squared. It's not really psi squared, but it's psi at x and psi at y. And when x and y get close to each other, that product has to become positive. So there's some sense in which these things have to be biased in one direction. And so it can't really be zero if we know it's biased in one direction. That's another vague way to understand why these corrections have to be there. Anyway, so I was happy about all this because it helped me understand something about the matrix elements that I didn't really understand before, which is that they can't really be Gaussian. There have to be corrections. I sort of always knew there had to be corrections, but I didn't know the corrections would ever be important. And here they are actually important and dominate the answer. And I'm also happy because by analyzing it in frequency space and putting a bound that's actually fairly easy to derive in frequency space, one can then reproduce the Maldacena-Stanford. Okay. Again, so that was my second and final newish results. Again, back to the ETH matrix element ansatz formula. An important question, which is still not fully answered, although a great deal of work has been done by many people. When does this really work? When are we allowed to use this and when are we not allowed to use this? We know that if a system is integrable, we can't use it. Although in so-called interacting integrable systems like the XXZ chain, there's still a version of the off-diagonal term that applies, and recent work by Marcos Riegel and collaborators on this is very interesting. The diagonal term in those cases does fluctuate. But you know, how big a perturbation do we have to turn on an integrable system to have the transition, and how does the size of that perturbation scale with system size? These are all questions that are still not well understood, and are of course opportunities for future work. Okay, that's really it. So ETH, that matrix element structure, explains, I claim, why StatMech works for isolated systems. An example where we have high mathematical confidence that that matrix element structure holds are systems we get by quantizing a classically chaotic system, and there's still a lot we don't understand. So that's it. Oh, and new tools, yes. Entanglement entropy and various other more sophisticated quantum information technology is yielding new insights, and things like the out-of-time order correlator, which was bypassed by the traditional quantum chaos community, I think, are important. And so, thank you.
Thank you, Mark. I guess we have some time for questions.
I'll ask a question. If one could imagine considering higher point out-of-time order correlators, is that interesting to consider? And presumably you would then be able to relate it to your higher point.
Yes, so all right, so is it interesting? I don't know. Can it be done? Yes. And so the Follini and Kirchen paper, they don't just talk about the 4-point correlator, they talk about any order correlator and develop this whole formalism. Their goal was also to understand the Lyapunov growth, but they didn't quite manage to do it. And so Chaitanya and I added this, which could really be considered a small addition of putting a bound on the omega dependence of this G function, and then showing that that's related to the bound on lambda. So yes, but I highly recommend their paper for the general analysis. Is it interesting? I don't know. To the best of my knowledge, no, which is not a very stringent test. No one has written down a higher point correlator that has an intrinsically interesting feature to it that shows up first in that higher order correlator. But maybe someone has done that and I don't know, or someone will do it tomorrow.
How it is related to random matrix theory, in particular with the approaches to dissolve the system of transport? Would they have done less sigma models or so on?
Yeah, well, so there's a long history of this. Boris Altshuler and Vladimir Apatov and various other people like that in the 90s started applying sigma model techniques to undisordered systems, to chaotic systems, with a sort of hand-waving justification. I think we saw some of why that's okay in Tomas's talk earlier today, where he added a bit of disorder and then removed it and showed that in the system he was considering, one could remove the disorder and the results remain. So clearly if one wants to average over disorder, that's a mathematically you now have a mathematical justification for calling things random matrices, because you put an actual random thing in your Hamiltonian, which you're going to average over. The subtle question is, when does that work even if you're not averaging over a Hamiltonian? And what we've learned in quantum chaos theory over the decades is that quantum chaotic systems often behave like random matrices in the sense that if you write the Hamiltonian in some natural basis, it, quote, looks like, unquote, a random matrix. Or if you write an observable in the energy eigenstate basis, which is what I've been doing, it, quote, looks like, unquote, a random matrix. Now, to what extent can looks like be made mathematically precise? I don't think we have a solid answer to that. It's one of these physicsy things that we know is true, but if you try to nail it down, it seems a little slippery to make it mathematically precise.
Is it possible to show whether thermalization occurs exponentially fast or with some other function of time?
Generically, no, because the thermalization time is controlled by that f of E and omega function. So do I dare try to reshare my screen? Sorry, I'm doing the wrong thing. Let's see, I guess I have to go out of Keynote. Reshare Keynote. Let me see here if I can find. Yeah, okay. So so this F2 object, this is, if we don't worry about the fact that the rho has been, which is a thermal density matrix, has been split into two pieces. This is basically a thermal correlation function in time of this observable. And what it turns out to be is essentially the Fourier transform of the absolute square of this F function, which appeared in the matrix elements. So the time dependence for this to do something it is controlled by the omega dependence of this F function. And the omega dependence of this F function is not universal. It depends on the specific system and the specific observable. So, you know, we can find observables with all different kinds of thermalization times. And indeed, we'd better be able to do that because we know that some things, you know, there can be collective modes of things that thermalize very slowly and so on. And so all that has to be possible. So the bad news is this general formalism doesn't tell us anything about that. We have to know what this F function is in order to compute something like a thermalization time. And that will be system specific and observable specific.
In the model Tomas had, what's the Lyapunov exponent? Is it maximally chaotic?
Oh, you'll have to ask Tomas that.
Yeah, that. Well, in my model, there is no small parameter, so there is no formal Lyapunov exponent because h bar is 1. So I mean, you always have to have small parameter in order to have exponential growth in OTOCs. So there is no Lyapunov exponent. I mean, that's why I'm interested about these models, because they are really non-classical, yeah, in any meaningful way.
Yeah, the exponential growth occurs over a finite range in time. And that finite range is minus the logarithm of some small parameter. Yeah. And so if you don't have a small parameter, you don't have a range in time where you can see exponential growth. And the classic small parameter is 1 over n in ADSC, or 1 over n squared.
Is there a case which is not a large n theory where you have that small parameter?
Yeah, Victor Golitsky and collaborators have looked at this in things like, I think, the kicked rotor, where they have an h bar that they've tuned to be small, right? They're choosing parameters so that their effective h bar is small, and so their 1 over n squared in the ADS CFT sense is equivalent to h bar. But they have to tune parameters, right? If they tune parameters, not in a bad way. I mean, you're choosing parameters because you want a system with a small h bar to study semi-classics. And again, this original intuition of Larkin and of Chinnikov that the exponential growth is akin to a classical Lyapunov exponent modulo some factor of 2 that seems to have disappeared in the transition from the 60s to the aughts. That's the right intuition, and so you need to have some sort of semi-classical regime defined somehow. And in ADS CFT, it's the semi-classics of the gravity dual that's important. And in these models studied by Victor, and I'm sure many others as well, it's that you set yourself up in an explicitly semi-classical regime.
I guess this kind of concludes the formal program, but I think we can leave the Zoom link open for if people want to stick around and chat for a while.